The latest from CERN, physicists are detecting signs of neutrinos at the Large Hadron Collider. We know that we have found neutrinos in Antarctica as well. The International Forward Research Experiment team was led by physicists of University of California in Irvine, and they achieved the first ever detection of neutrino candidates, and they were produced by CERN facility in Geneva at the Large Hadron Collider. The paper published in the Physical Review, researchers describe how they observed 6 neutrinos interactions during a pilot run of a compact emulsion detector installed at the LHC back in 2018. The co-author Jonathan Feng, UCI, said prior to this project, no sign of neutrinos has ever been seen at a particle collider. This significant breakthrough is a step towards developing a deeper understanding of these elusive particles and the role they play in the universe. Now, I, for one, am not a physicist. I don't know what role they play in the universe. He said the discovery made during the pilot gave his team 2 crucial pieces of information. Feng said first, it verified that the position forward of the Atlas interaction point at the LHC is the right location for detecting collider neutrinos. And second, our efforts demonstrate that effectiveness of using an emulsion detector to observe these kinds of neutrino interactions. They explained that their instrument was made up of lead and tungsten plates, alternated with layers of emulsion, and during particle collisions at the LHC, some of the neutrinos smash into nuclei in the dense metals, creating particles that travel through the emulsion layers and create marks that are visible following process. These etches provide clues about the energies of the particles, their flavors, tau, muon, or electron, and whether they're neutrinos or anti-neutrinos. Now, as Feng explains, the emulsion operates in a fashion similar to photography and in the pre-digital camera era. When 35mm film was exposed to light, photons leave tracks that are revealed as patterns when the film is developed. The phaser researchers were likewise able to see neutrino interactions after removing and developing the detector's emulsion layers. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box. He said, having verified the effectiveness of the emulsion detector approaching for observing the interactions of neutrinos produced at a particle collider, the Fraser team is now preparing a new series of experiments with a full instrument that's much larger and significantly more sensitive, he explains. Now, since 2019, he and his colleagues have been getting ready to conduct experiments with phaser instruments to investigate dark matter at CERN LHC. They're hoping to detect dark photons, which would give researchers a first glimpse into how dark matter interacts with normal atoms and other matter in the universe through non-gravitational forces. Now, for the life of me, I really still don't know why they're doing all this. Anyway, maybe if you know, please explain to me. Now, with the success of this neutrino work over the past few years, the phaser team, consisting of 76 physicists and 21 institutions in 9 countries, is combining a new emulsion detector with the phaser apparatus, and while the pilot detector weighing about 64 pounds, the phaser NU instrument will be more than 2,400 pounds. You can understand how huge it is. It'll be much more reactive and able to differentiate among neutrino varieties. Now, given the power of our new detector, co-author David Casper says, phaser project leader, and his prime location at CERN, we expect to be able to record more than 10,000 neutrino interactions in the next run of the LHC beginning next year. He said we will detect the highest energy neutrinos that have ever been produced from a human-made source. What makes phaser NU unique, he said, is that while other experiments have been able to distinguish between 1 or 2 kinds of neutrinos, This will be able to observe all three flavors plus their anti-neutrino counterparts. And Casper explains that there have only been about 10 observations of tau neutrinos in all of human history, but that he expects his team will be able to double or triple that number over the next few years. This is an incredibly nice tie-in to the tradition in the physics department here at UCI, Feng said, because it's continuing on with the legacy of Frederick Rains, a UCI founding faculty member who won the Nobel Prize in Physics for being the first to discover neutrinos. He says, "We produced a world-class experiment at the world's premier particle physics laboratory in record time and with very untraditional sources," Casper said. "We owe an enormous debt of gratitude to the Heising-Simmons Foundation and the Simmons Foundation, as well as the Japan Society for the Promotion of Science at CERN, which supported us generously," he said. Savannah Sivley and Jason Arakawa, UCI PhD students in physics and astronomy, also contributed to this paper. And this is by Physical Review and DOI, Physical Review, and it's on phys.org. Please leave your comments. Thank you for your support.